So this is number 52. Number 52, and we are in chapter 6, number 52. And I believe it's the one with the guy passing the hockey puck to a teammate. And one of them comes up short, and then the other one is supposed to make it. You're supposed to find the other velocity. And some things they keep the same, I believe, is the frictional force. Is that something they kept the same? Anybody remember? Reread 52 here while I set up the picture. Reread 52, page 177. I'm going to reread it too, just to make sure we got it. Yeah, all right, there we go. And we have the initial velocity of the hockey puck right here is 1.7 meters per second, and force of friction stays the same. They said the frictional force, not just the mu, but the mu would stay the same as well. So we've got force of friction staying the same, 1.7 meters per second, and here we're trying to find this velocity, and we've got corresponding distances. This one comes up at the halfway point. So I'm going to call this x, that's making it the other teammate, and this one will be half x, or x over 2. Is everybody all right with the, I need someone to check in with. Who can I check in with? All right, I'll check in with you. Are you all right with the x over 2 versus the x? So I got two cases here. I'm going to call this case 1 and case 2. I'm going to start to do this via a ratio. I'm sure you could solve it with substitution as well, but you'd have to notice that two variables multiplied by one another will end up being something you can substitute into the other equation. I'm going to try to do it with ratios, or at least start there, because that's how I would normally start this problem. Let me just double check here, make sure I actually hit the record button. Not that it matters, but we did. Look around. So things that stay the same, friction. Things that are different, definitely velocity and displacement. And we're trying to figure out what this velocity is. And you might start by saying, oh, let's go ahead and use motion equations. However, the chapter we're in would tend to let you believe that motion equations are not going to work. Is everybody all right with that? If you started with motion equations, there'd be some problems in here, I believe, or it'd be a lot more work. And so I'm going to start with not that, but taking a look at, we're trying to find a V work done. Because work equals FD, which equals change in kinetic energy. As long as we're calling this a height of 0, we don't have to worry about potential energy. So delta KE, there's no change in potential. Is that okay? We're all right with this idea? And in the case where we come up halfway short, or here, let's get a general result that relates this starting velocity to getting to the teammate. Now when it gets to the teammate, let's see. Sliding to a halt when an initial force. I think we have to make the assumption, here it's true for sure, that this V final is 0 meters per second, and here we got to assume that it comes to a stop as it gets to that teammate. So I'm going to say that this V final is 0 meters per second as well, so those two are also the same. And let's expand out this equation so we can apply it to the two cases and do a ratio. And I did this because one of the things that stays the same is the force of friction, which is the thing that will make the hockey puck slow down and come to a stop. In fact, if I draw a 3x diagram for the hockey puck, normal force, weight, are either of them doing work? No, because they're perpendicular to displacement. But the friction, hockey puck sliding to the right, the friction is going to the left. There's the 3x diagram. The only thing doing work is friction. Is that okay? Anybody else all right with that? So that's why I did this. If you weren't sure why I was expanding this out, it's because there's only one force doing work, and that's the frictional force. So let's go ahead and substitute some stuff in here. Work equals force of friction kinetic times the displacement. This is now specific to what we're doing here, and I'll put in the actual variables we used in a minute, which will also be equal to 1/2 mv final squared minus 1/2 mv initial squared. You all right with me expanding the delta KE? What is V final for both of these cases? 0. Is everybody all right with that? I'm going to try to simplify this formula as much as possible. So this is gone. So I have force of friction times whatever my displacement is equals -1/2 mv naught squared. That's my general result for any time someone's passing a hockey puck with an initial velocity, and then it's going to come to a stop, some displacement later. Very, very specific now, but I'm going to apply it to case 1, and I'm going to apply it to case 2. Before I do that, which one of these variables do I care about? No. No. Initial speed. Look at what we're trying to solve for. It says, what minimum initial speed should the puck have been given so to reach the teammate? So we're looking for this V naught right here, and I'll call this V naught 2, and now I'll define this as V naught 1. If I could answer the question of V naught 1 over V naught 2, if I told you that was 5, it's not. If I told you that was 5, could you solve for V naught 2? Yeah, so that's what I'm going to do the ratio for, and hopefully a bunch of things will cancel. Let's solve this for V naught first. So it'll be force of friction times the displacement times 2 over m, and there'll be a negative square root. Let's see if I did that all right. Oh, no, hold on. This is a negative, but no, it's not inside because I made a mistake. A physics mistake, actually. Friction and displacement. I have not accounted for my sign. Shame on me. Which way is the friction going? To the left. Which way is the displacement going? To the right. So the work done will be negative. So I should have a negative right there. Is everybody okay with that? And how did I catch my mistake? When I was starting to do the square root of a negative number, I knew I did something wrong. Well, no, it is possible, just not for the problems we're doing. Yeah, we don't have any imaginary numbers in AP Physics. Physics eventually can have imaginary numbers, but for weird stuff. Yeah, it's not that weird. So the negatives cancel out. So now we do get 2 force of friction times displacement over m for an expression for V naught that can be applied to both of these cases. So now I'll come back here and let's apply it to case 1 and case 2. So case 1, so I'll go ahead and write this. The 2 will be there. Force of friction. What's the displacement for my case 1? X over 2. All right. And then over the mass of the hockey puck, over square root of 2, force of friction. And again, same variable because they told us the friction stays the same. That's why I'm using the same variable. That's why I had it up here as, I guess I should put some K's on that. Be consistent, times the displacement for case 2, which we've put on our picture as X. All that over, square root a little bit bigger here, all that over m. There's a lot of stuff go away now. Yeah, the 2's cancel out. The force of friction cancels out. The x's cancel out. The m's cancel out. It all goes away except for this. And so that I hopefully don't mess up my algebra, I'm going to redo it over here. V naught 1 over V naught 2 equals square root of, we have a 1/2 right there. And I think everything else went away. And that canceled out, so that'd be a 1 over 2 in the numerator. So yeah, square root of 1 over 2. So there's what V1 over V2 equals. And now we can plug in our V naught 1, which was 1.7. And then solve. I'll grab a calculator. You guys can solve as well. Careful that you don't solve for 1 over V naught 2. Actually solve for V naught 2. So I'm doing 1.7 times the square root of, 1.7 divided by the square root of 0.5. And then I'm taking it to the -1 power. I don't know if that's right or not, but I got 0.41 if I didn't punch any numbers wrong. That's wrong? Okay. Now let me punch the numbers in again here and make sure. 2.4? 1.7 divided by, well, what was the actual answer though? 2.4? 2.4 meters per second. Did I not raise it to the right power? Did this work out to 2.4? Yes, for sure. Someone double check right now. Who has actually plugged in these numbers and solved? Today. And it came out to 2.4? Well, now what did I do then? Oh, I had this on the other side of the equation. I know what I did. Yeah, we're good. It's 2.4. You're right. We don't need to check. We're fine. Questions? I raised it to -1 power, but I pretended the V2 was over here. I don't know why. Go figure. It's the camera. I'm going to blame the camera. No, I'm just kidding. I videoed myself at least like 30, 40 times in the room. It's not the camera. Questions? The other way to do it, if you did it with substitution, you'd have to realize that force of friction times displacement, you would have had to, at some point, solve for one of those and then substitute into the other, solving for two variables. Instead of solving just for friction, you'd solve for friction times x. Get an expression, plug into the other equation. With a ratio, it just all cancels out. I think it's a little bit nicer. It's certainly a little bit quicker for me. It's a little bit quicker for me. Questions anywhere up here? The overall process of a ratio. If you recognize that a ratio will solve it, like when there's two cases and they're linked, in this case by friction being the same and the displacements being related, one of them was x, one of them was x over 2, get a really good picture with case 1 and case 2 and label all the stuff here. If a variable stays the same, keep it the same. If a variable changes, change it. That's why I had v01 and v02, because they were not the same. The v finals, just use v final because they were both 0 anyway. If you don't like the picture thing, still have two pictures, but then make a list of variables for case 1 and a list of variables for case 2, and then start going into the ratio. You might have gotten stuck. You might have figured out that this was relevant and solved and gotten something like this, then forgot the frictions were different. Then you'd have to go back and reread the problem if you had like friction 1, friction 2. Or if you just had x1, x2, go back, read the problem again if everything doesn't cancel out, and see if there's anything else you can do to relate. If that doesn't work, then try to find some other physics equation or start in a different location. Questions? Did they give us the mass of the hockey puck? So this cannot be solved with motion equations, I don't believe. If they gave you the mass of the hockey puck, motion equations could have worked here as well, because then you would have been able to solve for an acceleration, found the displacement, and go from there. Problem solving, if you're really in a pinch here, could you have made up a mass of the hockey puck? Yep. So on an actual test, if you want to make up the mass of the hockey puck and try this with motion equations, go for it. There's nothing wrong with that. There would just be an alternate solution.